Hello YouTube, DeVore here again, and today I'm going to be talking about the second task in the first module of the Integrated Math 3 curriculum out of Mathematics Vision project from Utah. This is the second task in our inverse functions unit called Flipping Ferraris. This is a task that's talking to you about driving. Most of my students who are in this class are currently driving, and something that we talk a lot about in driver's ed is if you are going faster, the more time and the more distance you will need for your car to come to a complete stop, which is why when you're on the interstate, you need to make sure that you are leaving room between you and the car in front of you for safety reasons. So this is looking at the relationship between how fast you're driving and how far you travel before you stop after hitting the brakes. First thing that you'll want to think about is what kinds of factors might make a difference in how far the car travels after hitting the brakes. A popular answer here is road conditions. It will take longer to stop if the road is wet or the road is icy than it will if it is sunny. Another thing is the state of your brakes. Make sure that you are going and actually getting your car checked every now and then. It will help you and your car stay healthy. And you can think of a lot more than this, but these are my two most popular answers when I do this task in class. So we're going to look at some of the experimental work done mostly by police departments and insurance companies so that we can accurately model the relationship between the speed of a car and the braking distance, which is how far it goes until it stops after you hit the brakes. Here is our dream car. I think it's actually this car up here. I'm not entirely sure. I'm not big into cars myself. But we have what's called a Ferrari 550 Maranello, which is an Italian car. Experiments have shown that on smooth, dry roads, the relationship between the braking distance, given as d, the speed, given as s, is given with this function right here. Speed is given in miles per hour, the distance is in feet, because we are, of course, in the United States. This would look different if we were thinking about meters per hour, or kilometers per hour, and in meters. Okay, so if we want our Ferrari to go 55 miles an hour, we want to figure out essentially the distance that we need to keep between the car and the car in front of us, which is essentially the braking distance. What we're going to do is we're going to plug this guy in. We know we're going 55 miles an hour, which, when we plug it into our function, looks something like this. Whenever you see something inside these parentheses, remember, from our original function that goes in place of s, that means in our function over on this side, we make sure that wherever we see an s, that 55 is going to go. When we plug this into our calculators, I would highly recommend doing this on a calculator just because the numbers do get kind of big. We end up with 90.75 feet. So about a little less than a third of the way across a football field, just for some comparison's sake. That's actually quite a distance when you think about it. 55 miles an hour, that's, state highway speeds. You need about a third of a football field in between you and the car next to you just in case they brake suddenly. And honestly, you should probably have more than that because there's always reaction time. So it might end up being closer really to 100 feet, but this is really a bare minimum here. Okay, so now our car is going 100 miles an hour. Now we're going to go through the same process here. We plug in 100 in for speed into our function. And you'll see me using parentheses a lot when I go through and do these. It's personal preference. You don't have to do that, but I find that it helps later on. Okay, I plug this into my calculator. It's going to take me 300 feet. That is a whole football field, guys, between you and the car between you, and it's going to need to probably be more than that. That's a lot of time, a lot of distance. So be careful when you're going 100 miles an hour, which is not street legal anywhere around where I live, so please be careful. Okay, if an average car is about 16 feet long, about how many car lengths should you have between you and the car in front of you if you are driving 100 miles an hour? Well, we know that our braking distance is 300 feet. And we're going to divide that into 16-foot segments so we can figure out how many car lengths that is. When I plug that in my calculator, I get 18.75 feet. So 18 3/4 of a car length, which for our purposes is about 19 car lengths. That's pretty close. It's about 19 car lengths. We're going to say that, see, it's not in feet, this is car lengths. I almost made a standard mistake here. Please be careful with your units. All right. It makes sense to a lot of people that if the car is moving at some speed and then goes twice as fast, the braking distance will be twice as far. Okay, so we're going to have our some speed. We're just going to call that S. Now, if we're going twice as fast, that means that we are going to S. We're going to plug that into our equation here. So if d of 2s equals 0.03 times 2s squared. Now, we need to be careful with our squaring here. Please, please, please do not simplify this to 2s squared. That is bad. It's a very common mistake. Please don't do it. Instead, it should look something like this. 0.03 times 4s squared. Now, normally, when we do this, we end up with just 0.03s squared. But now we have this extra little multiplier here. We have 4. That tells us that we're not going twice the distance. We're going to be going 4 times the distance. So you need 4 times the stopping distance. That's pretty insane. That you need 4 times the stopping distance when you go twice as fast. And that doesn't seem very intuitive, but I guess it makes sense when you think about it, that, when we were looking at on the previous problem here, we were looking at 55 miles an hour and 100 miles an hour, and it went from about 90 feet of stopping distance to 300 feet of stopping distance. So you can see it kind of in the equation that we did before. So now what we're going to do is we are going to graph this sucker. So we have, let's put a couple of points in here. We've got, if we do it by tens, it would probably be easier. So speed, distance, 0, 10, 20, we'll go up to 30. So if you're not going any speed, it's going to be 0 distance. And then if we plug in 10 into our calculator, we need 3 feet. For 10 feet, we need 12 feet for 20 feet. And then finally, we need 27 feet for 30 feet. So let's go ahead and start dealing with this. So I hate this small graph, just so you guys know. Now if I do 10 feet, so that's 1, 2, 3, 4. 1, 2, 3, 4, 5, 6, 7 for 20 feet. 30 feet, and then 40 feet will be off the chart somewhere. 1, 2, 3, 4, 5, 6. This would have been a good time for me to have a made-for-TV moment. That way you wouldn't have to watch me graph. So at 10 feet, it goes 3, so I'm going to say that's about there-ish. At 20 feet, it's 12 feet, so it's going to be there-ish. 30 feet, it's going to be at 27 feet, which is here-ish. So we can, it actually came out pretty well. You end up with a nice little curve. It looks something like that. My version is not very pretty. I apologize in advance. But you can get a pretty good idea on how this is growing. Now let's describe the features. Now features, to me, we always start out with domain and range. Now domain, remember, is our set of all inputs. Range is a set of all outputs. Our domain, well, the smallest speed we can be going is 0 miles an hour. So we start there at 0. And we don't know exactly how far our car can go. And I don't really want to make any guesses here. So I'm going to say that our speed can go all the way up to infinity. Same with the range. The smallest distance that we can have is 0 for stopping. And once again, I'm not going to try and limit how fast our car is going. Now, this graph is what we call always increasing. What that actually means here is that as we go from left to right, our graph is always going up. Always, always. And there's no maximum distance, but we do have a minimum. We have a minimum at the 0.00. So there we go. Those are pretty much our features. Okay. What if the driver was cruising along, suddenly hit the brakes to stop? She skidded to a stop and fortunately missed the cat. When she got out of the car, she measured the skid marks left by the car so that she knew that her braking distance was 31 feet. How fast was she going? Well, remember that for our original equation, we were entering in time and getting distance. Well, now we know distance. We just need to get our time. The way we set that up is we say she went 31 feet equals 0.03 s squared, s being our speed. That's what we're trying to do here. So I'm going to divide both sides by 0.03. That's my first step. I end up with 1033.3 repeating equals s squared. And when I punch that into my calculator, because I need to take the square root of both sides, I end up with s being about 32.1 miles per hour. So there we go. She was going about 32.1 miles an hour. Okay. I just realized that this has a typo in it. Okay, next problem. If she didn't see the cat until she was 15 feet away, what is the fastest speed she could be traveling before she hits the brakes if she wants to avoid hitting the cat? We're going to do the same thing here. 15 feet equals 0.03 s squared. Divide everything by 0.03. Get 500 equals s squared. The square root of 500. It's not going to come out to be even, unfortunately, but we can make an approximation. S is going to be approximately about 22.4 miles per hour. So basically she needs to be in a school zone, which, I mean, this makes sense. This is why the school zone speed limits are always around 20 miles an hour, is because 15 feet is still quite a bit when you think about driving on the road, especially if a kid decides to run out in the middle of the street.
Could you please come to the office? Joe Brown, to the office, please.
I wish I could turn off the intercom. Oh well. So we're on to part 6 here. So now we've got part of the job of police officers is looking at traffic accidents. They measure the brake distance. They calculate the speeds that they're going, although they often use different formulas to account for various factors such as road conditions. It wants us to create a table that shows the speed, the car was driving. Oh, so we want the distance to be the input, the speed to be the output. I'm going to go ahead and use what we calculated to make our last graph. So we start at 0, 0. Then we have 3, 10, 12, 20, and 27, 30. Now, you may have noticed that I literally just took the tables, my first table, and I flipped it over. That was on purpose. That should ring a bell from 1.1 on how I was able to calculate some of the things about dog food so quickly. So that should give you a hint on how these might be related. Just a thought. Okay, so now we're going to figure out what the function of this is going to be. And to find that, we can really look at how we figured out some of the stuff before when we actually had actual numbers. So remember that we took whatever our distance was, we divided it by 0.03, and then we took the square root of it. So there's our function. Right there. Easy as pie. All right, so now we're going to graph the function like we did before. We're just going to use the table again. So let's see. You can also feel free to graph these on Desmos or GeoGebra or something. I'm not really as concerned. I just want to get a basic shape here. Okay. So once again, I'm going to graph my points here. I've got 0, 0. I've got 3, 10-ish, 12, 20, and 27, 30. So here's what our graph looks like. And then we also need to describe its features. So we have domain and range again. So our domain, remember, we're looking at all of our possible distances. Well, smallest distance it can go is 0, and it can go all the way out to infinity. With the range, well, it once again starts at 0 and can go out to infinity as well. Now, let's look at these graphs side by side here. So here are the two graphs. You might notice that this one kind of curves up and this one curves down almost like a bowl. I wonder what would happen if you graph these on the same coordinate plane. It might look kind of cool, I think. So that's just something to keep in the back of your head. All right. Well, what do you notice about the graphs of SD compared to the graph of DS? Well, SD curves kind of downwards. It's not quite the best word. It's another word for this is it's concave down. That's kind of the fancy math term for it. And DS is concave up. That's kind of what I was getting about with the shape. It's kind of, does the bowl go like this, you know, kind of like this, or does it go more like that? That's really what we're going for. Now, remember that how I generated those graphs was I just flipped the inputs and the outputs, which means, of course, that DS and SD are inverse functions. Yay. We're going to be hearing that a lot. Okay. Consider our original function over the domain of all real numbers, not just the domain of the problem situation. How does the graph change from the original graph? Well, let's take a look here. What's going to end up happening is that our original graph is really just that part right there. When it says the domain of all real numbers, that means that now we have this whole side of the graph. And if you remember from Math 2, well, this is a quadratic function, which means that it's kind of have that bowl shaped, kind of like that. So it's going to add the left side of the parabola. That's what it's going to do. How does changing the domain of ds change the graph of the inverse of d of s? Well, something that's kind of interesting about the way that we did our graph originally. So it kind of looks like this, right? If we were to allow negative numbers like this, it would actually, if you were to plug it into decimals or something, kind of look like that. So it would add the bottom side, not really a great term, of the parabola. And yes, parabolas can be sideways. That's something that's very important in conic sections. This is actually a parabola just because of the shape. It's symmetrical and it has that bowl shape, thus it is a parabola. You are definitely more familiar with this kind, but this is also a parabola, just so that you know. Is the inverse a function? Well, we have an approximate graph of what this should look like. Whenever you're given the graph of a function and you want to know, well, of anything, and you want to know if it is actually a function, you can do what is called the vertical line test. The vertical line test basically means that we can draw a vertical line anywhere we want on the graph. And if our vertical line crosses our function more than once, well, then it's actually not a function. So here we have crosses twice, crosses twice, crosses twice. So our answer is that with this new domain, d of s is not a function because it fails the vertical line test. Now you may be saying, but here it's a function, here it's okay, but here it's not. What happened? Well, we changed our domain. We decided that we were going to not be restricted by the context of our problem, where we can have negative speed, which makes no sense to us on a realistic level, but mathematically that's generally okay. So when we restricted our domain to just our context, where we were just looking at positive distances and speeds, it was fine. But the moment that we opened up our domain to all real numbers and included negative numbers, suddenly we were in trouble. And that's something that does happen every once in a while. Sometimes we need to restrict our domain in order for the inverse function to actually be a function. That's something that you're going to be playing with more throughout this unit. So just keep this in the back of your head that sometimes one version of the function, say where your domain is restricted, suddenly becomes not a function when you open it up. All right, so that was the second task in the Mathematics Vision Project Integrated Math 3 curriculum called Flipping Ferraris. Once again, if you need any questions answered, please feel free to send me an email and I'll answer them as best I can. If you like what you see, please remember to like and subscribe. That does help me out, and hopefully I'll start putting some more of these videos up. I hope you have a fantastic day. Bye-bye.